Pluto's journey through space compels it to rise and fall in its orbit as it intersects with the paths of other celestial bodies, notably when it crosses the trajectory of Neptune in the farthest region of our solar system. Pluto, the intriguing and mysterious dwarf planet, is stirring considerable interest in the realm of astronomy. New findings indicate that Pluto might be on a potential collision course with Neptune, which is causing considerable anxiety among astronomers and space enthusiasts alike. Well-known figures like Neil deGrasse Tyson and Michio Kaku have raised concerns about the possible aftermath of such a cosmic encounter. But what has led Pluto to this possible collision with its neighboring planet? Additionally, what impact could such a celestial crash have on Earth? Come along as we delve into how Pluto's path crosses Neptune's, and why this orbital oddity is unsettling the scientific community. Initially classified as a planet, Pluto was later redefined as a dwarf planet due to its irregular orbit. However, despite this reclassification, Pluto still captivates the imaginations of astronomers and space lovers alike. Recently, experts such as Neil deGrasse Tyson and Michio Kaku have voiced concerns over Pluto's orbital path, which could bring it dangerously close to Neptune. This close alignment suggests that these two giant celestial bodies might interact in ways that could have significant consequences for Earth. Pluto's orbit is unlike that of other planets in our solar system, elongated and unpredictable. Since its discovery in 1930, Pluto has not completed a single full orbit around the Sun, which only adds to its allure. Unlike the more circular orbits of the planets, Pluto's elliptical path stands out as a defining characteristic of our solar system's structure. Another captivating feature is the tilt of Pluto's orbit, about 17 degrees from the plane of the ecliptic, which is sharper than that of any of the main planets. This combination of an inclined and stretched orbit adds layers of complexity to Pluto's motion around the Sun. One particularly fascinating aspect of Pluto's path is its periodic interaction with Neptune's orbit. For roughly 20 years in each cycle, Pluto's orbit brings it closer to the Sun than Neptune's, an occurrence that defies expectations due to the two planets' otherwise distinct positions. Notably, Pluto's orbit is not circular but shaped more like an oval, which causes significant fluctuations in its distance from the Sun. At its nearest point, Pluto is about 30 astronomical units, AU, away from the Sun, but at its farthest, it stretches out to more than 49 Australian dollars, double Neptune's distance. Pluto's orbit is also tilted at a key angle relative to the orbits of other major planets, further complicating its movements and interactions, particularly with Neptune. When Pluto and Neptune align in their orbits, their gravitational forces alter each other's paths. This intricate relationship underscores the interconnected nature of celestial bodies, with each one exerting gravitational influence that shapes the other's trajectories. In recent years, advancements in observational technology have allowed astronomers to track Pluto's movement with remarkable accuracy, offering a deeper understanding of its orbital mechanics and the potential effects on the stability of the outer solar system. Although a direct collision between Pluto and Neptune remains unlikely, the possibility still exists, fueling increased interest and concern among astronomers. Despite its diminutive size and distant location, Pluto continues to capture the attention of researchers and the public alike. So why hasn't Pluto collided with Neptune? The key lies in the gravitational interactions between the two bodies. When astronomers first studied Pluto's orbit, they were perplexed by its erratic behavior. Unlike most planets that stay within a consistent plane of orbit, the ecliptic, Pluto's orbit deviates sharply, adding another layer of mystery. The real puzzle came when scientists realized that Pluto's orbit intersects Neptune's. Yet despite this unusual overlap, Pluto's orbit remains stable. This phenomenon speaks to the intricate mechanics of space and the difficulty of predicting celestial paths. Understanding the gravitational interplay between Pluto, Neptune, and the Sun presents a significant challenge for scientists. Predicting these interactions is akin to determining future positions based on initial conditions and gravitational forces. For Pluto, the interaction between its orbit, Neptune's orbit, and the Sun's gravitational pull creates a delicate system that keeps its path stable. Terms like precession, libration, and VSOP variations help astronomers understand these complex dynamics. These concepts are vital for ensuring the stability of planetary orbits. When Pluto crosses Neptune's orbit, it is still about 90 degrees away from Neptune, which prevents any direct collisions. The process of libration ensures that Pluto stays safely on its orbit even as it approaches Neptune. VSOP variations, named after researchers like von Zeipel and Pacer, explain why Pluto's orbit might seem irregular but remains predictable over time. Even though the cosmos may seem chaotic, the forces at work tend to stabilize planetary orbits, reducing the likelihood of collision between Pluto and Neptune. This delicate balance highlights the sensitivity of celestial orbits to their starting positions. Even small shifts in a planet's velocity or position can cause significant changes over time. Through advanced computational simulations, astronomers have modeled Pluto's orbital movement, observing how minute variations in variables can dramatically alter its course. In the late 20th century, these simulations revealed that while Pluto's orbit might appear stable, it can still be subject to chaotic fluctuations. Even tiny differences in Pluto's starting position or velocity can lead to notable changes over time. However, Pluto's orbit has remained stable for billions of years, suggesting that despite its apparent irregularities, it follows a discernible pattern. Predicting the behavior of planets with such eccentric orbits is still a difficult task, with these systems being so unpredictable that long-term forecasting is challenging. Simulations are useful for estimating possible outcomes, but they also demonstrate the inherent unpredictability of celestial movements. Understanding Pluto's orbit is crucial, particularly when considering the remote possibility of a collision with Neptune in the future. Gaining deeper knowledge of these movements helps us understand the inner workings of our solar system and illustrates how even seemingly unstable orbits can be stabilized through gravitational forces. Pluto's strange orbital path around the Sun serves as a prime example of space's peculiarities. Unlike other planets, Pluto's orbit is not perfectly circular. At times, it ventures closer to the Sun than Neptune does, adding to the intrigue of its cosmic dance. Though the chance of a collision between Pluto and Neptune is small, it is important to recognize the powerful forces at play in shaping their orbits. Gravity, the invisible force that governs the movement of celestial bodies, ensures that Pluto and Neptune remain in their designated paths despite their apparent potential for collision. The study of Pluto's orbit offers valuable insights into the forces that govern space. What might initially seem chaotic is often the result of finely tuned gravitational interactions. Continuous research and observation are crucial for expanding our understanding of the solar system and beyond. The thought of a Pluto-Neptune collision raises fascinating questions about the potential changes to our understanding of the outer solar system. Even though we have made considerable progress in space exploration, such an event would underscore how much we still have to learn, signaling the need for further research. By investigating how larger planets influence Pluto's orbit, astronomers are unlocking important information about the behavior of the entire solar system. It reveals the ways that the positioning and movements of planets can affect the paths of other objects in space. Despite space's complexities, the possibility of Pluto colliding with Neptune continues to concern astronomers. This situation begs the question, how might such a collision occur, even though it seems unlikely? Neil deGrasse Tyson, a prominent astrophysicist, has commented on Pluto's reclassification as a dwarf planet. He sees it as a significant step forward in our understanding of the cosmos, reflecting how we continue to learn about the movements of celestial bodies. Tyson believes that events like Pluto's renaming engage the public in the pursuit of space science and emphasize how much remains to be discovered. Tyson, along with other researchers, has raised alarms about the potential dangers of Pluto's orbit, particularly the risk of collision with Neptune. He suggests that such an impact would be a monumental event for our solar system, causing ripple effects throughout the universe. A Pluto-Neptune collision could release vast amounts of energy, potentially shattering Pluto and sending debris into space, possibly colliding with other celestial bodies. Even Neptune's orbit would be disrupted by such an event. Michio Kaku, a well-known theoretical physicist, offers his insights into the celestial mechanics at play. Kaku emphasizes that studying Pluto's orbit is key to understanding the future of space exploration. He believes that by comprehending the gravitational interactions between bodies like Pluto, we can improve future missions and navigate space more safely, minimizing potential hazards. His work in string theory, an approach to understanding the fundamental laws of nature, could also reveal more about the forces shaping the universe. Kaku believes that studying Pluto's dynamics can unlock deeper insights into the forces that govern reality itself. Both Tyson and Kaku agree that monitoring a potential Pluto-Neptune collision offers a unique opportunity to advance our understanding of the universe. In particular, such an event could provide valuable data for string theory, which models the universe as a series of vibrating strings. Although the immediate effects of a Pluto-Neptune collision on Earth would be negligible due to the vast distance, the scientific benefits would be far-reaching, enhancing our understanding of theoretical physics and the nature of the cosmos. As researchers continue to study the gravitational influences exerted by neighboring planets like Neptune, the ever-changing nature of space becomes increasingly apparent. However, space remains full of mysteries. The three-body problem, where multiple celestial bodies exert gravitational forces on each other, is just one of the many challenges astronomers are trying to solve. Ongoing exploration of space is vital for expanding our knowledge of the universe and the laws that govern it. While the probability of planetary collisions is extremely low, the possibility persists due to the influence of gravitational forces. These forces can subtly alter the orbits of planets, potentially leading to collisions over time. One example of this phenomenon is the TRAPPIST-1 system, which contains 7 Earth-sized planets. The gravitational interactions between these planets can create orbital resonances, potentially destabilizing their orbits and leading to future collisions. Researchers are closely monitoring these systems to better understand how celestial bodies interact and how their paths can change. In addition to planetary interactions, rogue planets, celestial bodies that no longer orbit a star, can drift through interstellar space. These planets, once part of a solar system, can travel vast distances and occasionally collide with other star systems. However, the vast emptiness of space reduces the likelihood of direct collisions between rogue planets and other celestial bodies. Finally, when galaxies collide, the immense gravitational forces involved can disrupt the orbits of stars and planets. While planets might not collide directly, their orbits can be altered, potentially flinging them into space or causing them to collide with other planets or their host stars. Such disturbances can lead to the creation of new celestial bodies or even new stars. The late heavy bombardment theory suggests that around 4 billion years ago, an influx of impacts from comets and asteroids occurred, possibly caused by the movements of outer planets like Jupiter and Saturn. These impacts reshaped the paths of smaller objects in space, many of which were ejected into the inner solar system, where they collided with the Earth and other inner planets. Though these impacts didn't involve direct planetary collisions, they did play a significant role in shaping the surfaces and compositions of planets, especially Earth. It's even believed that these collisions contributed to the delivery of essential elements like water and organic molecules to our planet, creating the conditions needed for life. These ancient impacts serve as a powerful reminder of how gravitational forces from larger bodies can drastically alter the orbits and trajectories of smaller celestial objects. In conclusion, just as Pluto's eccentric orbit raises questions about a future collision with Neptune, the historical impacts of cosmic forces remind us of the dynamic and evolving nature of space. The delicate balance of gravitational forces governing planetary systems continues to be a central focus of research, helping us understand how our solar system, and the cosmos at large, has evolved and will continue to change over time. The potential for future encounters, whether between Pluto and Neptune or through other cosmic phenomena, highlights the complex interactions that drive the ever-changing nature of space.